Okay, so welcome to session 8C. My name is Olivier Martin. I'm working for CERN. So the session is about transport protocols in a wide area and storage area networks. And we have three speakers. The first one is Douglas Lees from the Hamilton Institute in Ireland. He's he's actually the author of one of the TCP variant called H-TCP, but he's going to speak about trying to compare the state of the various TCP proposals in terms of behavior in a high-speed network. The second speaker is Bartold Belter from PSNC, and he's going to discuss performance comparison of various storage area network solution. And the final speaker is Fanny Bick from Chestnut, who is going to present some new tools to help in debugging TCP performance problems. So Douglas.
Thank you, Olivier. And thank you all for coming along. I'd half expected the room to be emptier for the first talk after the event last night. So what I'd like to do is talk about some work that was joint with myself and some colleagues there at the bottom. There's some, and talk about some challenges in TCP congestion control and how we can evaluate that. So the history, there's a little bit of history in that TCP provides two bits of core functionality. One is reliable data transfer, so if packets are dropped, they'll be retransmitted. And then essentially a later addition to TCP was the addition of congestion control, and much of that stems from the late 80s when there were problems with congestion collapse inside the network, where if packets are retransmitted and are transmitted and dropped and then retransmitted, much of the work done by the network can be expended on retransmitted packets that are subsequently dropped, so that the net throughput is very low. And that was observed in the late 80s, the congestion collapse. And Van Jacobson at that point was hailed as the savior of the internet in coming up with a congestion control inside TCP, which has become part of the core functionality of it. Its purpose is to try and match the rate of the demand placed in the network to the network capacity, and it's viewed as an essential part of how the internet works at the moment. So lots of that core part of the functionality of TCP, much of it dates from 89, 90. And it stood us in good stead. Speeds have gone up by, I don't know, a factor of 100 or 1,000 or whatever in that time, and everything's worked fine, and they seem to continue to work fine. But there's a question: is that going to continue into the future? And there's good reason to believe that it won't continue into the future. As speeds go up to gigabit and above, then the congestion control algorithm inside TCP already is running into issues, a lot of which have been highlighted initially by the physics community, who've been looking for some years now, trying to do high-speed data transfers across the Atlantic, and the hardware is able to run it originally at 1 gig or 2.5 gigs or whatever speed it is now, but it was the software letting it down. So what I would like to do is that's led to a whole range of proposals for changes to TCP. Some more dramatic than others, and I need to somehow make some decisions about which ones are the promising ones that we should be looking at for further testing, which ones are candidates for actually rolling out. So that brings me to what I was going to talk about today. So what I thought I'd do is just quickly give a quick overview of the congestion control algorithm inside TCP to try and motivate the problems that there are. Mention some of the issues around testing and why it's far from straightforward to construct good experiments in practical terms, but also even in principle, because of there's issues about what we even mean by what we want TCP to actually do, and try and hopefully end on a more positive note that there is some hope here. So the guts of one of the key things in how the TCP congestion control works is linked to how the network itself operates. So current networks are pretty much all drop tail queues. So there's some information constraints. The sources at the edge don't know what sources and other machines are doing, and they don't know what the network's up to, except if it drops packets or from what it can infer from the edge. If we're thinking primarily of drop tail queues, then there's some very nasty properties. So what we have is TCP is trying to... That better? TCP is trying to match its demand on the network to the network capacity. So it needs to have some sense, so be able to figure out in some way what the network capacity is. And yet the queues are providing, the way the networks are constructed is that's quite a hard bit of information to get. If we send packets into the queue at less than the link rate, then they just go through. All we know is that they went through, that we're operating below the link rate. There's no information at all about what the capacity really is. And the only way to find out, get some indication about the capacity is actually to exceed it. So if we exceed it, then the queues will start to fill, and maybe we can detect that. And eventually they'll overflow and we'll detect a packet drop. And it's the packet drop approach that's used just now inside TCP. So that setup means we're quite naturally led to be inside our congestion control to actually have some probing action, try and ramp up the demand we place in the network until something happens, and then maybe back off or adapt that way. But the probing seems to be an essential part of getting information about the network itself. And so that leads to the algorithm that's used just now in the TCP, which is an additive increase, multiplicative decrease AIMD algorithm. And so it's all defined in terms of a C window, a congestion window, which is the number of packets in flight. So that's packets in queues and packets in flight along the fiber or wire. And what TCP does is it gradually increases the number of packets in flight, which effectively indirectly is increasing the rate at which packets are sent. And it increases it every time we receive an acknowledgement, it increases it by some constant factor. And the effect is over time, there's a roughly linear increase in number of packets in flight. And eventually we're going to exceed the capacity of the link, and a packet will be dropped, and we back off the congestion window there by half. So there's some numbers here. The increase rate there is 1 packet per round trip time in standard TCP, and that number there is you back off by a half. So that works great, sort of. So certainly for the last 15 years it's worked just fine. But it's starting to run into some problems, and the problems are very easy to see, actually. As we moved, and it's to do with large bandwidth delay products. So this is a dramatic example. It doesn't need to be quite as dramatic as this for there to already be notice a pretty serious performance loss. So there's going to be lots of sawtooths like this in this talk, because that's what TCP looks like. If we take the delay bandwidth product, so that's the bandwidth in packets per second times the propagation delay, and add on the queue, then if we've got a gigabit link and 1500 byte packets, then that's 200 milliseconds, which would be Europe to California. Then we plug in and we find that the delay bandwidth product would be about 21,000 packets. So that means the congestion window at which we get a drop is 21,000. We back off by a half. So we're down here at 10,500. And then we have to increase all the way up to 21,000 again before we're going to see another packet drop. And we know we're going at 1 packet per round trip time. So we've got not 11,000, but 10,500 round trip times. So that's going to take roughly half an hour. So that means the period here of the probing is taking half an hour, and it's just too slow. During that, half an hour without there being other packet drops, due to other traffic, due to corruption of packets and so on, it just doesn't happen. It's very rare. So that typically a packet drop will happen in here, and it'll bump along, and we never actually manage to fill the pipe, and the throughput's low. And that's not just me saying that. Here's some measurements. My nice picture hasn't shown up. This is some real data from the backbone in Dublin to Starlight in Chicago. So it's a gigabit. At that time, it was a gigabit link, and this was look at the time scale here. This is 1200 seconds, 20 minutes. You can see the length of the sawtooth that you can see in practice. The blue line is the congestion window, and the green line is the throughput. And taking remember this is a 1 gig link. Taking an average over 20 minutes, we only got 200 megs throughput with standard TCP, and that's with all the buffers increased and everything. No constraints inside the network. The constraint comes from the congestion control itself, and so that's pretty frustrating. We've got all this nice hardware. We've got the network's got this capability to run fast. If we were to run TCP, the UDP traffic, we've no problem filling this pipe, and yet our software, our transport protocol is letting us down. And so, although originally a lot of that came to the fore on long-distance networks, then, but actually we don't need long distance networks. As speeds go up, even a few tens of milliseconds is plenty to cause performance to degrade pretty seriously. And so lots of people, this has been known for 3-4 years now, lots of people have proposed changes. There's a half dozen or more changes being proposed to TCP, some more or less dramatic than others. And pretty much all of them are based around the notion that, well, it's too sluggish, we're not increasing our congestion window fast enough, let's go up faster, right? Which seems pretty straightforward. But it's not quite as simple as that, because we need to coexist with legacy flows on low-speed networks. The whole network isn't high speed, we have to be able to work on low-speed networks as well and coexist with legacy flows. So that means we've got some sort of mode switch where we're using the legacy value of increase in low-speed regimes and something new in high-speed regimes. And the nature of how to make that thing work, it wrong foots us quite easily, because it's very simple and obvious schemes don't work. And the interesting is for me, because my own background is in applied maths and looking at dynamics and systems like that, the failure mode of TCP just now is a dynamical failure mode. Everything's becoming sluggish and unresponsive, and the failure mode of most of the or at least not failure mode, the difficulties, issues that are highlighted by many of the proposed changes also are dynamic in nature, which is so that's how my own interest came into it. So here's one example. This was scalable TCP, and it proposed some changes to the increase here to make it to try and keep that period constant, regardless of the pipe size, of the congestion window size. And it seems originally it seems pretty straightforward and natural. And yet when you actually start doing tests, you find behavior like this. So what happens is that so we had one flow running here and a second flow starting up in a very simple topology here. That was the bottleneck. And they don't converge to fairness. We would think that if they've got the same round trip time, same bandwidth, that they should converge to fairness, and they don't converge to fairness. And it's worse than that. If I create, so these are simulation results, by the way, but I've got experimental results to back this up that I'll show later. During this period here, we created a cross-flow disturbance on this little path here to steal some bandwidth off the blue one. The green guy grabs the spare bandwidth, but the disturbance has actually ended here, and the blue guy doesn't manage to grab back. So what's happened is that here there's no. So this was one of the initial proposals for changes to TCP, and actually, and although it made sense and certainly makes things more aggressive, in the process we've actually disrupted the fairness inside the network in a pretty serious way, and there's no pressure at all to converge to fairness. So actually, it turns out that when we look a bit more closely, instead of being additive increase, multiplicative decrease, scalable TCP is multiplicative increase, multiplicative decrease. And we've known for a good long time now, 15, 16 years, that doesn't converge to fairness and isn't a viable proposition. So we learned some lessons. But here's another example. So I'm trying to motivate the fact that why we need to evaluate TCP and why this isn't TCP proposals and why this isn't a straightforward problem to solve, why there's issues here. So here's another proposal with what's called high-speed TCP, and there's an RFC out in this, and lots of implementations. And it suffers from something similar. It's sure it converges to fairness, it just takes a very, very long time. This is not even on a very fast or high delay link, so the time gets longer and longer, and I'll show you some plots later here. So remember, this is 5 minutes, 300 seconds is 5 minutes. So we're taking a significant amount of time for this thing to converge to fairness. And here, what the idea was to make the rate of increase dependent on the congestion window of the flow. So basically, what's happening is the guy who's got bandwidth becomes very aggressive. He's going up fast and backing off less. And the guy who's starting up, he's only got a small window, so he's being quite cautious. He's using a small increase and a small decrease. And it takes him ages to grab bandwidth off this guy who's being really aggressive. It's very, very, very slow business. So because you've created that asymmetry inside the network. So this sort of experience, because these have undergone quite a lot of experimental work and quite a lot of effort, and it only came out downstream that there were these issues with these proposals, which seemed on the face of it quite promising. So that motivates what this talks about. Well, first of all, given that there's lots of other proposals out there, and we're now worried that there might be issues with them, and how we're going to make decisions about which ones to explore more thoroughly, well, can we measure the performance in some sort of meaningful way? And that's not at all straightforward, because there's not a clear definition of what the performance requirement is for TCP or what we really want it to do. It's a community consensus sort of thing in a community where there's not a huge amount of consensus. And but we want to see, is it possible to construct tests that everyone could agree with, that relate to things that are practically interesting and are fair comparisons? It's always quite tricky to construct fair comparisons. And a second part of our motivation is, well, experimental testing's got to be what we do for things that we're interested in rolling out. But can we do it? But it's difficult and it's expensive. And can we do some sort of screening? Can we catch those issues with? So I showed simulation results catching issues with scalable and high-speed TCP. We didn't need to go to experimental testing. We didn't need to go to all that effort. We could have caught it at a much earlier stage by some simple tests. These weren't complicated or sophisticated tests that we needed to throw up the fact that there were issues. So can we learn from that to do some screening so that we can have a benchmark, a raft of tests that are very simple. They're not attempting to be comprehensive or exhaustive or any of those things. They're just trying to embody known issues and make sure that we've tested for things that we know are issues in advance. So we're trying to avoid wasting time and resources. So of course these equations are related. And I'm emphasizing here, this is all we're trying to do is thin out the field of candidates. So we're not claiming to be exhaustive, and so that's why I'd like to talk a little bit about in this talk. So there's been a fair bit of work on that by people at CERN, people at Stanford, and other places, on trying to do testing. People who are interested in actually operating them, and as soon as we try, forgetting the sort of philosophical questions just for a second, if I have a digression just for a minute, forgetting the questions of, well, what are the performance requirements and how can we measure them and all those things, there's some pretty serious practical issues in actually constructing experiments that are going to give any sort of meaningful results at all. And so here's two two issues that I think would be good to flag up because they've been learned the hard way, and so it'd be good for them to be disseminated. So none of my pictures work. Can you hit? So Olivier, there's my. So I've got a lovely picture there. That's very nice. Can I plug my laptop in? Would that do the trick? So it's the first of many pictures in that format, right? So is this just going to transfer over to? It's on my screen. So maybe I can talk about what the picture would look like so that when we see it. Thank you. So here's a trace, and this is from a testbed network that's all instrumented, and we know exactly what's going on. So notice that its speed isn't particularly dramatic, right? And it's running Linux. So this is a standard Linux kernel with all the buffers big, everything sorted. And these are actual C-Win traces. This is an instrumented stack, so we've been poking around in the guts of it to try and demonstrate some issues here. So if we're interested in doing experiments, the natural lots of people, Linux is the platform of choice. Is the platform of choice for current high-speed experiments. And so typically people who are proposing changes produce a patch against Linux, and the obvious thing is to go away and do experimental test comparisons of these patches. But it's not as simple as that because of this sort of issue. So if you run a standard Linux kernel, and then you get very, very strange things happening. So look at the Cbund here. The red guy is a Cbund. I was showing I saw this before, wasn't I? Look at these dead patches. Look at that one, completely dead. The green line that you can hardly see is the sequence number of the packets as they're transmitted, and you can see that it's completely stalled. There are no packets transmitted during that dead time. So there's a serious performance. So something strange is happening when we try and run Linux at high speed. It's a standard Linux kernel at high speed, and that's my screensaver. That's the problem. So let me show you these numbers here. So this is instrumenting the queue between the device driver, which is receiving incoming ACKs. This is at the sending machine, and then putting those, the device driver puts those in a queue, and then the network stack reads those out. And this is marking the length of that queue. And the queue is only 300 packets. So what's happening here is this fills up. And in Linux, what happens is when it fills up, a throttle action is introduced where all subsequent packets are then dropped. The queue's full, the system's under stress. We'll throw away all packets until the queue actually empties. So what that means is that once that queue fills, all subsequent ACKs coming back in from the destination machine are thrown away. The ACK clock, the whole stream of flow of packets that's keeping TCP up running is completely broken, and we get these really, really serious timeouts and disruption to what's going on, to the throughput and to the transfer, and the throughput takes a nosedive because of this as well. So, and basically the problem is that there's quite a lot of processing needed on ACKs coming back. If they've got selective acknowledgement information, there's quite a lot of bookkeeping needed done to keep track of that. And everyone uses selective acknowledgements for these kind of tests because there's generally multiple drops. And so this is a plot showing distribution of processing times for ACK packets coming in on the slow path only. So that's once we've got a packet drop, not the forward path when everything's looking good. And at 250 megs and the size of packets we're using, we need to process the packets on average before that line, 550 microseconds, or else we're not keeping up with this rate at which packets are coming in. And we can see actually, if I calculate the numbers on, I don't think this is the right one actually, is it? Maybe it is. The numbers here, it's a log scale. 50% of the ACKs actually take longer than 50 microseconds, and so we're running into serious trouble. We just, the processor, the sending machine just can't keep up with the rate of that it needs to process ACKs and keep the transfer going. And this is in a high-end Xeon machine, so it's not a hardware issue, it's purely a software issue. So one of the things that ourselves and others have looked at is, well, you know, how can we compare congestion control algorithms when the basic network stack itself is unable to run at a reasonable speed? And also that means that, so typically patches that people provide also contain quite extensive changes to the network stack itself that are unrelated to congestion control. And it means that doing comparisons between those patches is fraught with difficulty. You don't know what you're comparing. Maybe someone's been a smarter kernel programmer with a very efficient implementation and someone's been less smart. So that so you end up comparing not congestion control algorithms, but the actual quality of the implementation, which is maybe there's some interest in that, but it's certainly not the sort of things that I'm interested in looking at. I want to look at the behavior of the congestion control algorithms themselves. So, given those issues, and they're pretty serious issues, then so we've been looking at various changes to the network stack to try and improve performance. And so they're not functional changes, they're algorithmic changes inside the Linux stack to improve the processing. You can see here that with fairly straightforward changes that we can push the time, we can push this distribution all to the left, and nearly all the packets, something like only 0.01% or something, take longer than 50 microseconds with these changes, and suddenly everything works again. So we've got a nice clean plot. The sequence number, the transfer is not interrupted. This is the sequence number proceeding. The queue never builds up, so everything's working fine. And so it's so what we've been doing. So the first lesson I think that comes out of this is when comparing different congestion control algorithms, it's quite important to control for changes in the network stack implementation. Make sure that the stack implementation is up to the speed you're running at. So this is 250, which is what all the tests I'll show are for. And I'll use a common implementation and only vary the congestion control algorithm, because otherwise it's hard to draw any conclusions at all about what you're looking at. And that's a hard one lesson. And there's a second lesson that's the less hard one, but it's worth pointing out. It's just for historical reasons, if nothing else. And that is that if we're wanting to test something, test the congestion control, again, my focus is all on congestion control, then we better make sure that the congestion is out in the network and not inside the server itself. So here, this is actually our first trace we ever took on the data tag network between Geneva and Starlight in Chicago. And this was a machine with a 1 gig interface card running down a 2.5 gig link. And what happens there, so the bottleneck is inside the interface card of the server. And so what happens is that we're handing off packets, we're probing for bandwidth, TCP is probing for bandwidths, it's handing packets off to the driver, and the driver, this is all inside one machine of course, eventually will say, I can't cope with that anymore, and return an error flag back. And pretty much everyone's ignores that, will modify the network stack to ignore that feedback from the driver saying slow down, and they'll keep hammering it. So that what happens effectively is that the congestion control is switched off, and all you're doing is testing the efficiency of your driver. So this is running at 960 or 940, whatever it is, 940 I think it is, which is simply the line rate with Ethernet framing of a 1 gig link. So all you're doing here is testing that you've got a good driver, it's flat out, and you never invoke congestion control. So if you see tests saying, I'm taking 10 machines with 1 gig cards and driving them down a 10 gig link, then the congestion is always inside the servers, and we're always seeing this sort of thing, and it's no test, it's a test of capacity, it's a test of the drivers, it's a test of the hardware, but it's surely a test of the congestion control. So with those sorts of things in mind, and some history here, this is discussion now. So these are proposed performance measures, and what I would like to try and do is demonstrate that we can actually see something interesting here, because potentially these things like if we've constructed our experiments so we're doing fair comparisons, what should we be comparing is the obvious next question. And I've listed 4 things here that on the face of it aren't controversial, I don't think, but actually once you dig down in them are potentially really quite controversial. So fairness, if we've got competing flows, the failure mode for scalable and high speed and other proposals occurs not with a single flow running on a link all by itself, but when we've got 2 or more competing flows and they're trying to divvy up the bandwidth between them. So the issues when we've got competing flows and fairness there is certainly a core issue. Friendliness, so backward compatibility with legacy TCP flows, we wanted to work if we wanted to roll it out into the public internet, then we have to worry about those things. Efficiency, for sure, that's the whole, we want to be able to use the hardware capacity that's available to us, and that's what's motivating us to make changes in the first place. And responsiveness, it's a dynamic environment, flows starting and stopping. A lot of the focus here is on long-lived flows and bulk transfers, but of course there's plenty of web traffic out there and so on. So we're interested in how things perform in a dynamic environment. And on the face of it, those things seem straightforward, but as soon as we start talking about fairness, for instance, people say, well, what do you mean by fairness? Well, what metric are you going to use to measure fairness? And those things lead to quite thorny philosophical arguments in which no one can agree. It's the sort of thing to have a discussion of over a pint late at night. So how can we avoid those issues? How can we actually come up with tests that people will think, yeah, that's useful, that's not meaningful, and that is meaningful, and it doesn't offend sensibilities. It's not relying on a specific view of the world. So the approach we've been taking, we propose is, well, one way of dealing with that is let's take what we have just now as a baseline. We quite reasonably well understand the performance of what we have just now. Let's take that as a baseline and compare any changes against that. That's a non-judgmental thing to do. We're just going to measure performance of what we have just now, measure performance of what we're going to get, and look at them, right? And see if we can draw conclusions. So that's one thing, to try and sidestep the whole issue of what we mean by performance metrics. And another thing is that it's important that we're considering not just high-speed networks, but a range of speeds. So in the test that I'm going to show here, we've been looking from 10 megs up to 250 megs. So certainly not the whole range, but an interesting range, as it turns out, I think. A range of propagation delays from quite low to quite long, and a range of queue sizes, the things that we know influence the behavior of standard TCP. We should be exploring across a grid of data points and not just focusing on a single test and a single data point, and looking at performance across a range of network conditions. So I'm certainly, remember, I'm not claiming this is exhaustive or complete. It's a first step, and we're trying to do screening and at least try and see if we can make some progress in understanding what's going on, making some decisions about what proposals are promising, which ones are less promising. So, or maybe need some more work. So the starting point, if I'm taking that viewpoint, we want to do something simple or not controversial. Let's start with the simplest case we can think of. Let's take a simple dumbbell setup like this. This is a lab network I'm going to show, where we've got a bottleneck link here, 2 TCP flows transferring across those 2 arms. We can vary the bandwidths and the delays and the queue size. So let's take the simplest case, which is where the propagation delay for both is the same. They've got a shared, they're running the same protocol, they've got a shared link. So that's the simplest possible setup we can imagine, I think. So we can say some things immediately about what we expect from that. It's so non-controversial. One is that we expect 2 competing flows with the same round trip time, the same stack, going across the same paths essentially, to be fair with each other. That we'd expect them both to divide up the bandwidth equally between them, I think. Certainly that's what standard TCP would do. And we wouldn't expect that fairness to be sensitive to the bandwidth, the number of users, or the queue size, or any of those network properties. And so that was the first test we ran. And so let me give a flavor. I'm not going to, because there's a lot more tests than are on the web. You can see I'm just going to talk about a couple of tests that are quite informative, I think. So these are measurements taken. This is our grid of RTT or measurements. What we're doing is plotting the ratio of the throughputs of 2 competing flows competing along the same path and doing it for different stacks. So the big thick line is our reference. That's what standard TCP does. And so it's pretty much fair. That's the same plot. It's just different scales. Here, the rest are various proposals. Not all the proposals that are around, but some of them that we've run tests for. And so look at this graph here, for example. We can see that in the simplest possible test already, we're throwing up something that sets alarm bells ringing. Here's scalable TCP. We can see that it can be horribly unfair. We get a factor of 20 unfairness between flows with the same round trip time, everything symmetric. And that's certainly surprising. And it harks back to what we were talking about the failure inside TCP that doesn't converge to fairness. So that was less surprising in a way. We were expecting to be able to throw up issues with that. That was a known issue in doing these tests. What wasn't known, for instance, is that fast TCP also seems to have some complicated fairness issues. And I'll show some time histories to try and dig around a little bit more at that. And some of the others, so for example, this one here is high-speed TCP, the one I was showing at the start. So it's fine at low round trip times, but as we increase, something's happening. And the same with BIC here. So we can, but less seriously. So let's have a look at time histories, because that somehow seems much more compelling when you actually have highlighted the problem. And so these are CWIND time histories for 2 of those points for scalable. And we can see what's happening is that as we increase the round trip time, it's not converging. It converges achingly slowly to fairness. It doesn't even converge after 10 minutes. And then at this point, by the time we've got to 162 milliseconds, it's not converged at all. And actually, if I've got longer ones, it really, the green guy's getting no bandwidth at all. So our time histories and our data points all match up, and we're seeing in our experiments, we're revealing issues that we knew already, which is good, because we want to embody issues that we know are out there and make sure we don't repeat those mistakes. This is the time histories for fast, and we see something. So I'm not going to. There's some ideas of what's going on here, but I don't think we've got time. So something strange is happening. This is on a low-speed link. So all we're doing is low latency. All we're doing is increasing the latency, and we can see the behavior changes pretty dramatically. We've got quite a complicated behavior here. Something strange where you get convergence and then loss, then divergence, and odd things happening. And that's why we're seeing those data points scattered around without going into too much detail. And so if we think about the other 2 points, which were less serious, these guys over here, we can do something similar and get the same sort of idea that we know there's issues with high-speed TCP. We're expecting to see something here. And again, we see this slow convergence that becomes more pronounced as the round trip time increases and everything becomes more sluggish. So as the delay bandwidth product increases, which we know is the difficult situation, and that's results for BIC, another version, which also is quite sluggish. And so when we're seeing unfairness, is because they haven't had time to converge over 10 minutes. So even that simple test already seems to be seeing something interesting, which is great because it's not controversial, and it's very straightforward. And it's if you don't pass that test, then we should be going away and having to think again, I would argue. There's another, if it flows with different round trip time, I'm out of time, I think. We can say interesting things as well. Very quickly, this would be standard TCP with 2 flows with different round trip times, and we can see that many of the new proposals are very unfair between flows with different round trip times. And so, just to make that a point, rather than make that concrete, this is a trace of the good put of two flows with so a factor of 8 difference in round trip time, and I wouldn't want to be this red guy, right? He's getting virtually no throughput. Another guy, it's a 250 meg link, so he's getting basically all the throughput. So that, there's clearly issues there. So just to wrap up, the message that I was wanting to get across were that using standard TCP as a baseline seems quite a useful thing. It's sort of non-judgmental. These plots, which aren't using specific metrics, which are hopefully reasonably non-controversial, are still quite meaningful. When you look at them, you think, I'm getting something useful out of those. That even these very simple tests, really so simple that people haven't run them, I don't think, in the past, are very revealing, and that some screening is possible, very simple screening is possible. And the last thing, of course, is that experiment design is not trivial. Unless we're careful in setting things up, it's hard to draw any conclusions at all from experiments. And so a lot of the effort going into these tests was actually setting things up so that we were confident that things were working right. And I guess that's another reason for using measurements on standard TCP, because we want to make sure we know how it should be behaving, so we can compare our measured behavior and hope that it's agreeing with what we expect. And if it doesn't, that's a signal that there's some issue in our experiment, probably. Thank you.
Well, many thanks for this. This very interesting talk. I think we're still time for 1 or 2 questions. Are there any questions? Okay, so maybe we leave that to the end. So the next speaker is from the TNC, the performance measurement for in storage area networks. So Bartel.
Can you hear me now? Okay. My name is Bartek Belter. I'm from PSNC, and I would like to present a performance assessment of distributed storage area networks. Just a few words about the agenda. In the first part of my presentation, I will make a short introduction to storage networking, and then I will show today's storage networking challenges. In the next part of my presentation, I will present IP storage as a new approach to build distributed storage area networks. And finally, I will present the results of our experiments in Polish National Network Pioneer. Before I start talking about storage networking challenges, I should introduce several important definitions. First of all, what is storage networking? According to Storage Networking Industry Association, it is defined by the practice of creating, installing, administering, or using networks whose primary purpose is the transfer of data between computer systems and storage elements and among these storage elements. Going further, the network that interconnects these storage devices with associated data servers is usually known as a storage area network. Last years, we can observe a total explosion of storage data. Every day, more and more information is coming to our company. Every day, more and more data is produced by supercomputing centers located around the world. How to keep this data? How to store this data? How to exchange? How to share with this data? This situation triggers appearing of many high-performance computing centers with their own storage area networks. And here the question appears: how to integrate them in a single distributed, scalable, high-performance system? The construction of such systems remains in the focus of many research projects. The main building blocks for such infrastructures are HPC centers and connecting them broadband optical networks. However, the major problem in integrating them lies in the fact that usually HPC centers use different technologies, not always applicable in our optical backbone. Additionally, traditional storage networking introduces its own limitations. In example, maximum distance range to transfer data using fiber channel technology is limited to 10 kilometers. In the contrary, for another storage area network protocol, the maximum distance range for SCSI is limited to the tens of meters. We can extend our storage area network over short distances using optical links and fiber channel technology. But how to interconnect remote locations? The answer is IP storage. IP storage is a new technology with trying to integrate advantages of two different worlds: IP world and networking world. With IP storage, you can extend your storage area network anywhere IP network is present and required bandwidth is available. There are three new IP-based protocols used in IP storage applications. They are significantly different, but they all provide common function: transporting block-level storage data over an IP network. They allow to integrate existing storage infrastructure and existing networking infrastructure without any modifications. Now I'm going to present the results of tests performed in Polish national network Pioneer. The main goal of this experiment is to measure how the distance affects overall performance in distributed storage networking. There are many vendors offering IP storage solutions, but for our test, CNT and Cisco solutions were used. Because the goal of this test was not to compare the vendor solutions, but just to check the possibility of interconnection remote sun islands. In my presentation, in the next slides, I will skip all vendor-specific information. As you can see, 9 locations in our network were chosen as measurement points. The maximum distance between them is over 1,500 kilometers, and appropriate round-trip time value is about 20 milliseconds. Here you can find a detailed description of our testbed. As a client machine, a PC workstation with gigabit Ethernet control and fiber channel interface was used. As IP storage elements, as I said before, Cisco and CNT solutions were used. And as a data storage, 2 arrays connected with a software write were used. Our measurement scenario includes the following actions: setting up the connectivity between distant IP storage devices, mounting remote partitions, running benchmarking tests, and tuning up the transmission. Our tests provide reading and writing performance for measured with listed here software, benchmarking software. It should be mentioned now that our tests were performed in live production network with no quality of service guaranteed. Okay, now I'm going to present some selected results from our tests. Here is the first result, reading performance measured with Tivoli Synergy Performance Benchmark Util. During our tests, we found that, as it was expected, the overall performance decreases. But for us, interesting was the fact that it has a linear relationship with the distance. Our tests provide us an answer that interconnection of distant HPC centers is possible even over 1,500 kilometers. Here you can find, here you can see the influence of a write acceleration option on the overall performance, generally speaking, writing performance. When write acceleration option is enabled, write I/O latency is limited, is decreased by minimizing the long distance latencies. Write acceleration option enables the host to start sending data without waiting for transfers-ready SCSI confirmations. It eliminates the delay caused by multiple transfer-ready commands needed to be exchanged over the IP network using standard fiber channel over IP transmission. As you can see, write acceleration option does not affect the reading performance, but it produces interesting results for writing performance. As you can see in the last point of this characteristic, over 1,500 kilometers, writing performance increases twice in comparison to standard fiber channel over IP transmission. Here you can see the CPU load measured in during our test. As it was expected, the CPU load for iSCSI protocol is higher than CPU load for fiber channel over IP transmission. It happens because during our test, iSCSI software driver was used. That means that all SCSI commands sent to remote storage should be handled by this software driver and, in fact, by client's machine CPU. I think this behavior could really affect the iSCSI protocol performance, and especially for short distances where small latencies allow to transmit data with highest efficiency. Here you can find the result for copying of huge file between storage elements. In fact, because this file was sent from the storage device to def null device, it presents reading performance. Before the file was sent from the storage to client's machine memory was cleared in order to avoid caching this file in memory. As we can see, it presents a good linear relationship with the distance. Now I'm going to provide some results from MySQL benchmarking test. MySQL is a very popular open source relational database. On the SourceForge pages, we found a simple benchmark for such relational databases, and we have just used it. For testing purposes, 4 tables were created. 3 of them are quite small and use no more than 2 megabytes of storage capacity, but the main table is huge table and stores over 1 gigabyte of data. Although you have checked MySQL database against many queries, I will provide here only few selected, including loading data into the database test, simple query test, and index generating. It should be mentioned now that database and database file system was created each time before a new test was started in order to avoid some kinds of caching and keeping the state of database in temporary files. First, MySQL benchmark loading data into the database. This operation performs sequential reading from input file and sequential writing into the database. As we can see, this operation scales linearly with the distance. In one measurement point, we found some unexpected results. It could be caused because of some problems with the network. Because, as I mentioned before, we have performed this test in production network without any quality of service. Next, MySQL database benchmark. This operation is a simple query and reads from 2 tables only. And as we can see, even non-complicated query introduces significant decrease of the performance between local data processing and remote data processing. By local, I mean the first measurement point. Next slide provides us results for index generating. It's more complicated request, and this operation reads from all tables in database and stores a small amount of data. As we can see, more complicated query also introduces a significant decrease between in comparison between local and remote measurements. This is the last slide with test results I'm going to present today. It shows the influence of the block size, client block size parameter to the IP storage performance. Here you can find few characteristics for fiber channel over IP transmission. Here you can find characteristics for iSCSI transmission. And here is the comparison. We found that using small block size parameter, there are no significant differences between iSCSI and fiber channel over IP protocols. We found also that the greater block size, the better performance, but too large block size decreases overall performance twice. It happens because used block size was greater than our software write chunk size, and each I/O request was stored in 2 chunks instead of single. And this is the reason why overall performance decreases twice. At the end of my presentation, I must say a few words about tuning of IP storage transmission. During our test, we were able to configure several parameters, including maximum window size, selective acknowledge option, and maximum transmission unit. It is recommended that a maximum window size should be greater than the product of link bandwidth and measured round trip time. But please notice that if you choose too small maximum window size, your communication and your transmission could be throttled by the impact of long-distance network latencies. If you choose too large maximum window size, more data have to be retransmitted if TCP packets were to be lost. Next parameter, selective acknowledge. TCP implements reliability by sending acknowledgements for each received data segment, and these acknowledgements are sent for in order received data segments. In case of packet loss or packet reordering, there are no possibility to acknowledge these data segments. TCP selective acknowledge, by using TCP selective acknowledge, receiver is able to acknowledge these received out of order data segments. During our test, we have changed the configuration of our backbone network. We have changed the maximum. We have enabled jumbo frames on our network switches on the path, testing path, and we have changed the maximum transmission unit on IP storage devices to 2148 bytes. It must be mentioned that important for iSCSI protocol, hardware TCP offload engine was not tested during this test, and also fiber channel over IP compression was not tested. Now I'm going to provide some conclusions. As it was expected, the overall performance decreases with the increase of the distance. For us, interesting was the fact that it has linear relationship with the distance. Assuming this linear relationship, it's easy to calculate how overall performance decreases with the increase of the distance. And we found that for each 100 kilometers of the distance, performance decreases about 4 megabytes per second. And for every millisecond of latency, performance decreases about 3 megabytes per second. But please do not keep these calculations as a reference. It's just my thought. During our test, we found that interconnection on remote HPC centers is possible even over 1,500 kilometers. We also found that using vendor-specific features like write acceleration could considerably increase writing performance, especially is writing acceleration option is more and more efficient with the increase of the distance and latency. I must say a few words about interoperability. During our test, we found some interoperability issues, and I think that it's a big wish only that IP storage products from one vendor will interoperate with those from another, even if IP storage protocols were published by IETF some time ago. Okay, thank you very much for your attention.
there any questions before we? Yeah.
Willy Huber from Switch. It's not maybe not a question to you, but to the audience. Okay. I know that certain people or the high energy physicists doing experiments with data transfer even over faster pipes and over long distances as well. And it would be interesting to hear about experiences made so far. How are the high energy physicists able to transfer their data from the LHC experiment, which is to start in a year or two? Maybe Olivier knows about some recent results.
I wonder, is Sylvain Rabot there? No. No, he's not. He mentioned yesterday the well, I have to say we are using special paths. So in practice, we are making experiments on uncongested 10 gigabit, basically dedicated pipes. And we have been approaching now, and also a number of other groups like the University of Tokyo have been approaching the limit of the PCI-X bus, which is in practice, because of the segmentation, 7.5 gigabit per second. So we have been able to have flows running, single flows, memory to memory, running at that speed. And from disk to disk is still hard work, but the latest figure are 550 megabytes disk to disk from Geneva to California, but we hope to improve that significantly. The next step in our case is to get our hands on the new server with PCI Express buses, and really trying to generate a single stream at 10 gigabits. So that's the aim. But of course, we are in a fairly comfortable situation because we are not forcing congestion. And actually, at the end of the session, I will have questions for Douglas. So, are there other questions? Maybe you want to comment? No? Yes, there is one more.
I know you were experimenting performance, but do you know that how do IP storage protocols deal with security?
We have not performed a security test during our measurements, and I think it's an open issue. It's I know that IP storage transmission could be secured with IPsec, but I'm not in this topic right now.
Maybe I can answer on this question, that we are using this test using a dedicated VLAN. If there is dedicated network for the fiber channel transmission, it is so safety as the VLAN is safety for this. In this case, we see that the transmission made on this low-level protocol cannot be disrupted by some hackers on this.
And no performance
No, the VLAN was pure, that without any some limitation on some mechanism. So security for this.
I know that security introduces some overheads to the transmission, and I think it's very interesting to measure this overhead is, how big this overhead is for IP storage transmission.
Okay, any more questions? No? Okay, so let me thank you again very much. So the last speaker is Sven Ubik from Chestnut, and he's going to present new tools to help debugging TCP applications.
Does it work? Yeah.
Okay, thank you. My name is Sven Ubik, and I would like to present you two tools which can be used to debug TCP performance problems. When we encounter poor performance in end-to-end communication, we should realize that the problem can be anywhere in the communication path. For instance, the problem can be in low available bandwidth in the network. It can be caused by faulty network component which loses packets. It can be a property of transport protocol which behaves in suboptimal way, or we may have reached limits of PC hardware speed, or it can be a limitation in application or some operating system overhead. And when searching for a possible place where performance is limited, it is usually necessary to use a combination of monitoring tools which are based on active monitoring, which sends tests packets into the network, passive monitoring, which observes directly user data, and monitoring, which looks what is happening inside the end host station. In this talk, I am going to concentrate on perhaps less investigated part of monitoring, which deals with TCP transport protocol behavior using end host monitoring. Common way to look what is happening during TCP connection is to capture packets with TCP dump tool and to analyze and visualize the connection using TCP trace and exploit tool. This is a very useful approach. However, it has certain unpleasant properties, such as TCP dump normally requires root access to tap network interface, and TCP trace is a follow-up analysis. That is, we only know what happened in our connection after the connection has ended. And also, TCP dump quite heavily loads CPU. That is, if we run it on the same machine which is used to send or receive our connection which we are monitoring, TCP dump can either influence the monitored connection or it often loses some packets. I would like to present two complementary tools called bulk and AIMD patch, which can be used to monitor TCP performance. Bulk is a tool to measure TCP throughput in a similar way as iPerf does. That is, it sends a heavy stream of TCP packets and measures how much of them pass through. However, it is complemented with synchronous monitoring of TCP runtime variables. It works in such a way that after each write call on sender or read call on receiver, it reads kernel variables using any available socket options. The kernel provides lots of options categorized into different levels. There are IP socket options, TCP socket options, and so on. And this tool can be used to read any selected options. Important property of bulk is that it doesn't require any kernel patch and it doesn't require root access. Any user can run it using his own account in user space. And it provides real-time analysis during the connection and incurs, I think, low CPU overhead. And additionally, it can work with AIMD patch to get some motion and to configure AIMD parameters, as I will show later. So how to use bulk? You start it on a server side and on a client side, which is directed to host name of the server. And you can use a couple of command line arguments. Two most important of them are S and G, which can be used to set or get any socket option, as I mentioned. You can use either mnemonics for existing socket options, or you can use their numbers, which can be used to set and get any possible future socket options which can be added to the kernel using some patches. The most important option to set is probably the size of sending and receiving socket buffer, which limits the size of TCP window. And the most important option to get is probably TCP info option, which provides various information about TCP connection. This is just a list of some options which can be read using bulk. And this is example how it can be used. We can get a TCP info option and add a list of its members which we want to read. In this case, we are monitoring time development of sender congestion window and SS trash variables, which are the two most important variables directing congestion control, as we already heard in this session. You can see in this picture that the connection experienced some packet loss, which resulted in halving congestion window and some serious packet loss, which even resulted in dropping connection to slow start phase. You can't get this information from TCP dump because these are internal variables inside TCP. You can get it using, for instance, Web 100 kernel patch, which is commonly used. But using bulk, you can monitor these characteristics without any kernel patch and without root access. Or you can use bulk to read vScale's member, which show what was the initial window scaling factor announced by the two communicating parties, and which determines how much the receiver advertised window is scaled in order to use larger congestion windows. You can also get this information from TCP dump, but that requires root access to capture the connection. There are a couple of other interesting command line switches. You can reverse the transfer so that data is sent from server to client, and you can specify a block size to be sent by write call or to be expected from read call. This is very important because, as I said, TCP variables are read after write or read call. That is, by specifying block size, we effectively adjust time granularity in which we can monitor these TCP variables. If we specify block size so small that it fits into one maximum size segment, then we can monitor TCP variables per segment after sending or receiving each segment. Or we can specify block size 1 megabyte and get a coarse grain monitoring. You can also request several connections either in parallel or in sequence during one test. And if they are in parallel, then you will get information about TCP variables for each connection separately. And let's look how much additional CPU load is imposed by using bulk. We can try to use strace utility with bulk, which reads a TCP info option to get number of system calls and the percentage of CPU time spent in those system calls. And we can see that about 80% of time was spent in write, this sending data, and about some 13% was spent in calls which were used to monitor the connection. There is also some additional load which is not in system calls, which is in user space by processing obtained information. But this is, on the other hand, the most heavy case when we set block size so small that there was one call to write with one retrieval of TCP variables per each segment. The other tool I would like to mention is AIMD patch. This is a separate thing which can be used together with bulk, but bulk can be used on its own. It doesn't need any patch. This patch allows to configure parameters of additive increase and multiplicative decrease of congestion control in TCP. As we already heard this session, congestion window in TCP increases linearly after receiving each acknowledgement packet, and it's decreased multiplicatively when the packet loss is detected. In standard TCP, it's increased by one maximum segment size segment per acknowledgement and decreased to half when packet loss is detected. And those various fast TCP implementations use different parameters of this additive increase, multiplicative decrease, congestion control. Using this patch, you can configure the speed of congestion control individually for each connection. So from one machine, you may have a couple of TCP transfers, and each transfer can use different congestion control. And you can also use this patch to switch on, off, and monitor usage of congestion window validation and reduction options, which are also used as part of congestion control. One way to use it is per system-wide. That is, you can use syscontrol standard command to write to new TCP AIMD system variable and configure congestion control behavior for all new connections opened on this machine. So this is one way, and the other way is that the application can configure speed of congestion control of each of its TCP connections using standard setsock opt system call, which uses a new TCP AIMD socket option, which is provided by TCP AIMD patch. And just to show example how you can use this patch, you can do experiments with different congestion control parameters used on different network paths, and thus find out how TCP behaves under different conditions. In this test, we send the data from CESNET in Czech Republic to Switch in Switzerland over a path which had round trip time 40 milliseconds, which required to set socket buffers to about 4 megabytes. And you can see that after a few seconds, connections stabilized on different throughputs for different parameters of congestion control. Of course, this is not for free. When we use more aggressive congestion control, we get more of available bandwidth, but it can obviously be at the expense of fairness to other existing connections. The main message about this patch is that it allows experimenting with congestion control, and you don't need to load different patches and reboot the kernel. You can just configure congestion control of individual connections during operating system runtime. And final slide, you can download bulk and an IMD patch at this address. And some future directions which we see, we want to add monitoring of hardware resources, CPU, memory, bus in end host PC, either using performance API or other tools. And we would like to provide bulk as a downloadable PC agent, so that people should be able to download that to their PC and make monitoring of health of their connection to the remote site. And that's it.
Any questions to Sven? Yes.
You are talking this bulk tool is using get socket option after write or read. It is possible to use it when send file system call is used on Linux.
No, this tool, this is a combination of throughput measurement and monitoring of this testing connection. So the tool includes inside write and read calls and these getSock opt connections. So it doesn't use the call which you mentioned, but okay. Of course you could add this functionality to other application. We one thing we consider is to implement this monitoring option to standard iPerf, because people are used to iPerf, and or it possibly could be it should be possible to provide it as a patch, or not as a patch, but as a set of routines which can be added to some yours application. to monitor conditions of your applications.
Any more questions? Actually, I have a question to Douglas. So I think there has been much progress in the understanding of TCP dynamics over these very high-speed networks. And there are many proposals, but there seems to be no progress in the consensus on which is the next generation TCP, which will be delivered by various vendors. So I think we are basically making very little progress. So if you could comment. Yeah, it's the...
So you ask hard questions. I think that, so this is just a personal take on it. My take on it is that at the start, did you say 3-4 years ago, there was I guess there was a feeling that this was a small change to TCP and quite straightforward. And that maybe that's what the lessons that have been learned in that time is that this is quite a significant change to TCP, and maybe the first, although there have been a number of tweaks to TCP over the last 10, 15 years, this is the first one that goes to the heart of the algorithm and actually makes a serious change. So this is quite a big deal. So that's been part of I think what you're seeing, that there's been an adjustment in expectations and a realization of the difficulty of the problem. Another part of it, though, is I think that although for me perhaps it feels like progress has been slow, my feelings of progress is happening. That things like I was talking about today, about how to construct good experiments that are allowed to draw conclusions, and I'm hoping that a consensus will develop around at least the evaluation, and that itself will allow things to move forward. So I'm cautiously hopeful that things over the next year or two will start to, there'll be some more progress evident. I think perhaps it's not too visible publicly at the moment, but my feeling is that there's some progress happening. Perhaps it just feels slow from a user's point of view.
Well, let's hope, yeah. Okay, any more questions? Well, if not, I would like to thank again all the speakers for the very interesting talks. And also, if you could think about filling in these online evaluation forms, which are helping the program committee to evaluate